All right. So today we'll switch gear a little bit. Now that we talk about both the GPU, DRAM, memory hierarchy, caching, virtual memory, we basically kind of cover the traditional topics, including some of the non-traditional ones like the GPUs and the DRAM that are a little bit more in detail than a typical like computer architecture class. Right now, I'm gonna switch gear and move on to one of the topics I want to kind of talk about. These things that we talk about today will not go on to your exam. They are a little bit more along the line of like, okay, these are things that you can do to squeeze out performance, right? Uh, there are stuff that I'm gonna talk that really discuss about like GPGPU application, which is basically application we write designed for the GPU. There are going to be topics about how to handle the cache in a different way, how to actually handle the way we fetch the instruction in a different way to make things faster. So today we'll be focusing on performance essentially, and it's a lot about the design. It's hopefully what I'm hoping for today is be a lot more like Q&A styles where you ask me questions related to some of the topics we talk about, and we will go through discussion. So the first thing that we need to discuss now that you learn how the GPU works. One of the things that I kind of want you to get out of this class is essentially these things. When you need to write an application on a GPU, because I expect that most of you ended up will be writing software, right? And code running on a GPU might be potentially one of those software. Fundamentally, if you think about the GPU is in order processor that are pretty slow. There's no branch prediction. There's not a lot of cache per threads. Doesn't handle code branch well at all, right? You don't want branch in your code. There's no prefetcher. We'll talk about what is a prefetcher in a few slides. The clock speed is slow. And it uses SIMD and fine-grained multithreading to make up for all these downsides, right? So if you blindly port a CPU program to GPUs, good luck with that. Basically, it's likely to be slow. And keep in mind that if you have an Intel CPU, right, and even the AMD CPU, like these typical CPU also supports SIMD instructions. So you can essentially write the program in the SIMD manner. Sorry, my cats are like running around behind me. Keep in mind that basically you can do this on a CPU as well. So if you want to utilize SIMD and you know that your code is not as parallelizable to the point that you have thousands and thousands of threads, maybe it's a good idea to use a CPU, right? So the first thing you need to know is you need to know the program really, really, really well, right? Know all the algorithm involved, know all the data structure involved in your program, and know if you can parallelize your data. And you want to make sure that your algorithm can be parallelized. Otherwise, it's not going to run efficiently, like in any way efficiently on the GPU at all. Like they will suck on a GPU. That's how frank I have to be. And parallel algorithm is the thing. So if you're curious, definitely talk to Ajahn Kanat. He's like the world expert on this topic. And I think he ran a class last semester that is basically parallel algorithm. And that could be interesting for some of you who might want to try like high performance computing. One more thing I want to make sure you're aware is with the GPU, the program counter points to the same instruction for multiple operations. So they have to, basic operation has to be similar. Low branch divergence, low memory divergence, and it's packed a lot of similar instruction together, right? And to be honest, these are really, really, really maps well with a lot of applications you have nowadays. And one more thing that you need to be aware of is it's by nature that these GPU hardware company, they don't really open source or open anything, right? So to be honest, like as far as I've seen, there's like a few more open source libraries and things that you can check from the AMD side, but for the NVIDIA cards, good luck with that. The CUDA compiler, the thread block scheduler, the warp scheduler, it's all these are kind of like black box. We know to some extent as an architect like how they works, but these are things that can happen to your code, and scheduling might happen in a different order than you expected, and the results either can be faster than you expected or slower than you expected. There are actually a lot of active area of research on the GPU, right? One thing that is pretty active right now, but it's hard. Like one thing I need to mention that this particular topic is pretty hard, is that you can improve programmability. Anyone want to define what is what is programmability? Can someone help me define that? Are you here? Yes, whether you can program it or not. And in general, programmability also talks about how easy it is to program. If you look at C versus Python, who would prefer programming in Python? If you don't care performance, who would prefer Python over C? Yep. So basically everyone, including myself, like when I need to script something quickly, I would just do that in Python. It's a lot easier to get the code out. And if you don't care performance, if you're okay waiting for like a few minutes, then it's fine. So improving the GPU in a way that is easy to program is always going to be beneficial. Right now, so one of you here tried CUDA programming before during the OPL class last semester, Brandon. So I'm sorry if I need to point your name. I just want to say that, hey, that's awesome that you try things on a GPU, and you might have realized that it's come with a lot of constraint, right? So there's a lot of research right now going into how to kind of relax those constraints, how to make it a little bit easier so you can kind of use something similar to C language, and then with some hints, you can parallelize things automatically, things like that. Another active research, which I'm actually personally involved in, are memory management. Right. So the first bullet point is actually having the virtual memory. So I'm going to talk about this particular kind of research now that we talk about the GPU that I did in a bit basically next week, and unified virtual memory where you need to migrate data between the CPU memory and the GPU memory. So these things are not efficient. That's like how flat out I can tell you. It's not efficient. It's there to improve. The first bullet point is improve programmability for sure, right? It make my life as a programmer easier. It's a CUDA malloc, CUDA memcopy, kernel launch, CUDA memcopy, and deallocate. I just do CUDA malloc manage and kernel launch. Magically, everything hopefully works, but it's not fast, right? So there's a lot of research going into how to utilize the GPU memory better. System building for GPU is also something that I'm trying to do as well. Basically, can you treat the GPU as its own compute element, right? Why do the GPU need to rely on the CPU's OS all the time? What are the minimum functionality support that you require to run a fully function program on the GPU without the CPU? Can we bypass some of the CPU OS calls to make GPU faster? Basically, these thing impacts. Oh, sorry, all right, sorry. I'm so sorry, guys. I just adopt a new kitten and he is running around like crazy. Uh, Yeah, right here. So it was him running and hitting a wall. Uh, yes, he did hit a wall. Actually, he hit a wall multiple times now. I hope he doesn't have concussion. No. Yeah, cut stream coming. Uh, he might like climb me. It happened before this morning. So yeah, sorry. So having a GPU running on its own, bypassing some of the high overhead like OS calls, right? Why are they high overhead? Basically, the OS is a program when you have to do things like interrupt handling. GPU interrupts and CPU interrupts, they all share the same scheduler, so the scheduler has to figure out, okay, who to go first. The problem is the GPU has its own processor, right? GPU has its own processor. Why bother? Well, you should just be able to say, hey, GPU, you can go first because you're just waiting. Like, you're not doing anything, right? So there are things like that that you can improve the GPU performance. The key thing is how to enable this, which kind of means that you need to go and hack the kernel and try to figure out, okay, what's the best way to support it. So that would be like the key innovation and the key contribution on these third bullet point, which is system building for GPUs. The last thing also I actively work on in the past 3 years going into the future is how to share the GPU in the cloud. Things like performance isolation. What does performance isolation mean? It comes from two words, performance isolation. I want to be able to run a program and I don't feel whoever is running and sharing my GPU, right? I want to be able to use the cloud server and don't really have to realize that, okay, whoever else is running and sharing that same computer is slowing me down. You want this isolation so that you can guarantee if I pay this much money, I should expect this much performance on my program. This is a huge topic in operating system and a big company that have cloud environment. There's a big research going into this direction at Amazon, VMware, Intel, IBM, basically Microsoft, all the companies that have data center. This is the one topic that they care about these days. And it's not like the only topic, but it's one of the more important topics that they want to enable. The second thing is memory protection. So this is kind of like already being supported in the current generation, but it's not as good as having the same virtual memory on the CPU. The reason behind that is because of the third bullet. You don't have the OS. So the last sub bullet, the memory protection, is kind of like a combination of system building for GPU and the sharing of GPU in the cloud. Self-advertisement, sorry, but like if you are interested in any of these bullet points, definitely let me know because at least in Thailand, I'm the only one who look in this direction. I can guarantee you that. Inside Asia, I'm the only few people who look into the GPU design because that's my thesis, right? So if you're interested in this direction, let me know. Because there's a few things that I would love to be able to improve and get the performance gain that I feel like the GPU deserves. And now let's switch gear a little bit. Any question about the GPU before we kind of move back to the memory hierarchy? Okay, then let's talk about the memory hierarchy. Recap. When you have a multiple CPU core, well, we are not going to talk about multiprocessor yet. We'll talk about that next week. There are a lot of issues involved with multiprocessor that has to do with the hierarchy, but let's stick with the hierarchy as we know it for now. You have a core, you have the L1 cache, you have a share L2 cache, and you have the DRAM, right? Recap. Any question about hierarchy before we move on? All right. So what we want to do now is, well, can we improve latency in the sense that can we make sure our data access is faster? Why do we care? Because the latency typically is the one that kills the performance, right? Pipelines stall for a long time because of memory access. No useful work is done if you're waiting for the data, and accessing data offship also consume more energy. So there are multiple things you can do to avoid latency. First of all, it's a concept called prefetching, which I'm going to talk about as a simultaneous multithreading. I'm going to talk about simultaneous multithreading. I'm not going to talk about fine-grained multithreading because this will be the third time I talk about it. Then the SIMD, which we already talked about. SIMT, also what we already talked about. So we'll skip those three topics, including a GPU. And then there's a VLIW, very large instruction windows that we'll talk about this at the end of this lecture. So let's talk about prefetching. Can we guess the next data load? Anyone want to make a statement that I can predict what is my next access if I see certain patterns? So how many of you use an array or a linked list to program? How common is an array in your program? Is it everywhere? Is it only one or two array per program? Or do you somehow like, I don't know, use functional programming and never use an array? It's everywhere. Yep. So I have a strong belief that array is basically everywhere. It's efficient. It's not, it can be not so space efficient if the things in your array is a bunch of zero, but there are ways to go around that problem. There's like different way you can represent the data such that you eliminate certain things, but it's everywhere. You write a program, I definitely can tell that there's going to be an array in there somewhere. A linked list is not as prominent, but they are there in many types of application. Graph, for example, you might be representing graph using pointer. It might not be a full-blown linked list, but it's close. Right? It's a node that points to another node. Binary tree, right? So it means that we can guess what data a program might need next. Anyone want to take a guess? Why is it the case? So let's say I have an array. Let's say I have an array. Do you think it's easy if I know I'm accessing A of 0 followed by A of 1? What is the likelihood? What's the next access that I'm going to do? If I'm accessing A0 and then A1, what's the most likely? Yeah, A2, right? Or it can be like A0, A2, and then A4, right? It will have a pattern. So the key point here is if you're dealing with arrays, there's so many times that you're accessing in a certain pattern, right? Pointer chasing, let's say you have a linked list. If I'm on the second element, what is the next one? What is the most likely next element that I'm going to access? I literally have one option. I need to go to the next one, right? And that pointer never changes unless you insert something in, right? But then when you insert something in, you know where the next one is, the next pointer. You just look at the pointer, you know, okay, this is the data I'm going to access. So these pointer chasing also have a predictable pattern. Is graph predictable? Okay, let me ask this question. Let's say I have a graph and the graph is dense. Basically, it means that I have a lot of neighbors. Is that predictable where I go next? Let's say I want to move around in my graph. It's actually not as predictable, right? Because for the graph algorithm, somehow you need to check what are my weights and you go to the weight that has certain range of value. So graphs are not as predictable compared to things like array or linked list, right? But still, when you're dealing with certain data structure, some of these are predictable. So it means that we can bring them to the cache, right? Because we know what are we going to access next, so we know which is the next cache block that I'm going to access. And we can do this ahead of time. The first technique is called the stream prefetcher. Basically, bringing things into the cache ahead of time is called prefetching. It's fetching the data. Prefetching means that I'm going to fetch the data before I know I need it. So if you see consecutive cache accesses, you fetch the next block. That's basically the stream prefetcher. Right? The next block is likely needed, and you can prefetch them to add, basically prefetch adjacent block of data. Why would that be useful? So let's say you see AF0, then AF1, then AF2, and then AF3. And let's assume this is still in the same cache block 1. What you might do actually is say, okay, I'm doing this A0 and 1 and A2, so I know that I'm likely to need cache block 2, which has A4, A5, A6, and A7, right? You bring this in ahead of time. This is the stream prefetcher. The pattern that we go through right now, 0, 1, 2, 3, 4, 5, is called streaming. It's streaming to consecutive pieces of data. Any question about the stream prefetcher? All right, so with that knowledge, the next thing you can do is what we call a stride prefetcher. What if my pattern is like this? A of 0, then A of 4, oops, A of 4, then A of 8. So it's not like 0, 1, 2, 3, 4, 5, 6, 7, but you still see the pattern. The pattern here is every time you go for elements. Or you can do this. A of 0, A of 2, A of 4, A of 8, A of 16, right? I guess A of 1 here. Basically, it's go 2 to the n. These also have patterns, right? So if you have this still predictable strides, you can basically, instead of stream prefetcher, which always fetch the next block, you fetch them in strides by using the history, right? By using the history. The way you can do this is you basically, one thing you can do is you can do a diff of the current accesses address and the last accesses address. If the diff is the same range, then you fetch them. You know exactly where to fetch next. Any questions so far? You actually can do this in assembly in the Intel x86. In the Intel x86, you have this instruction called prefetch. And then there's a number that goes here. The number represents the cache level of the address. So basically, it's an address afterward. It will tell the CPU, go get that address, put that in the cache level that you specify. Prefetch 1 means I'm going to prefetch into the L1 cache. Prefetch 3 will prefetch them into the L3 cache. You can write this code in the assembly, and the processor You opportunistically do this when you see the code prefetch certain address. It will try to prefetch that address as long as the cache is not heavily contended. The next thing you can do is what we call the Markov Prefetcher. So let's say you are traversing a tree or a linked list. Things are not in strides. Right? They do have patterns. You know exactly where to fetch next, but it's not the next address. It's some random cache block. So if you know the current pointer, you likely know the next block, right? You likely know the next block. So the idea from the paper in 1997 is basically you can prefetch using a Markov model to compute. Basically, you can develop a Markov model to compute the probability given the certain pointer that you are at right now. What is the next pointer that I'm going to access next? Anyone want to guess why this would work in a tree or a linked list? Why would Markov model be able to predict where do I jump to next in tree or a linked list? Any thoughts? Do you know what's the Markov model? Okay, you're not sure. Basically, Markov model would allow you to predict. Let's say you have a node that can go to two directions. This is part one and part two. Markov model would look at the history whenever you are here. So I'm going to use a different color. Whenever you are here, how many times you go there versus how many times you go there to the top and the bottom part. Then this we translate to a probability of going to 1 versus 2. Yep. So basically, given a pointer that we are at right now, right? Let's say it's a node in a tree, you would use the history to develop and to train your Markov model to know what's the likelihood that will go to the left or the right side of my tree path. Once you train enough, you can develop a model saying, hey, there's a 90% chance I'm going to the left, so I'm going to prefetch the left. And this is a technique used by Prefetcher. Anyone want to take a guess on why this might not be as effective in nowadays computing where the data is huge? So Markov model requires a table. The table would be basically as many as pointers that you want to predict, right? The problem with the Markov prefetcher is first of all, it will take some time to train, right? It will be too slow to train if the data is huge. The next problem is that it's going to take a lot of memory. Like the table will be huge, and that area can be used for something else. So this is not really cost efficient to apply this. But still, it's a technique that's has been discussed back in the day, like around 25 years ago. So, any question about prefetching? One thing I can tell you, prefetching is actually used a lot for training and inference for machine learning whenever you need the GPU. One thing that are common is you would prefetch the next sets of data from the CPU memory to the GPU memory ahead of time. This way, the kernel that's on the GPU will be able to have a new fresh piece of data whenever they need it. Right? So this is a common techniques in nowadays like computing, where a lot of data would occupy the main memory, and a lot of data would occupy the cache, and a lot of data would occupy the level 1 cache. So I'm going to skip the background on threading before we go to simultaneous multithreading, because we talked about this on a GPU lecture. Basically, you want to maintain multiple contexts, multiple threads in hardware. Simultaneous multithreading is basically when one thread is stalled because of the main memory or the L2 cache or L1 cache, the CPU will switch to another thread. This is done to keep the pipeline full. And then the trade-off is basically you need to figure out when do you want to switch and how do you want to switch. We talked about this on a GPU lecture. Any question about why simultaneous multithreading might be beneficial for your performance? This is the only slide that I feel I might put this on the exam. The rest of the slides here are like fair game. It's all like discussion. This is the one that this is I think the second or third time I talk about SMT. It's actually available on your CPU and you can use it. So these might go on to the exam. It might not. I don't know, but it's a fair game for me to put these things on the exam. So any questions from this? Okay, and start to live feed my cats behind me right there. All right. So let's wrap up the GPU related stuff. And let's switch gear, come back to out of order processor. From the exam, by this point, you might have realized that, hey, out of order processor is complicated. I'm sure you don't want to implement out of order processor on your lab, right? So fairly speaking, when you have out of order processor, it requires a large instruction windows. So basically it's complex and costly, right? Why is that complex? You need a lot of transistor to perform scheduling, check dependency, and support data parallelism. Back in the day, where you don't have the luxury of having really small transistor, back in the day, there's an architecture called Decoupled Access Execute, or DAE. Again, this is not going to go on the exam. I want you to know like some historical context and how to get out of order processor in a cheaper way, because I envision that something that been proposed back in the day might come up in the IoT devices, because it makes a lot of sense. It's actually allow you to compute things quickly, but without a lot of cost, right? So as I said, out of order is complex, too complex to implement back in the day. This is like 70s. What if we allow data access and data execution to be done across two instruction streams? So you write a program on the ISA, and the ISA basically allows the processor that would just say, I want these data, and another processor that say, okay, now that we have the data, these are the add, multiply, subtract that I need to do. This is called decoupled access execute processor. Why are they calling decoupled access execute? You decouple the data access part and the data execution part. This is proposed in 1982, and this is basically wrapped up in a journal in 1984. Basically, the way it works is you write a program. When you write a program, you then use the compiler to generate two instruction streams. The two instruction stream would then use if else control flow. If data is ready, do this. If data is ready, do this. They use control flow to synchronize the data, the access part, and the execute part. How many of you heard about things like scatter and gather? Yes, no. I mean, it's okay to say no. I never heard about scatter and gather. So the parallel programming concept requires you to get a lot of data so that you can process it, right? Let's say you want to write a parallel for loop, you want to write nested parallelism. One of the things that each of the iteration requires is the fact that you should have the data, right? Basically, you want to make sure all the threads has the data that it needs to compute. And everyone with me so far, basically, if you want to write a program, you better have the data ready in an array, in certain data structure, typically an array or vector, right? With me so far? So a gather operation basically means that I'm gonna go and gather all my data. Let's say I'm looking at a graph, right? A graph, and say I'm just compute this part of the graph as this part of the subgraph of my big graph. The gather operation will go and gather all the data involved in that subgraph for you, so that when you run, you execute on the data you gather, and then you scatter it back. You scatter the data back. So it's kind of like I'm gonna gather all the data so I can compute in parallel, and then I'm gonna scatter it back. So is it more? Is this high level explanation clear for you guys? Yes, no, maybe, not sure. Everyone pause. I'm not sure. So as I said, this one go on to exam. Just want to like talk about certain things that is similar to this decoupled access execute model. Okay, assuming that either you all like slept in the past 2 minutes, or I would assume you understand what I talk about. Otherwise, you should say so right now. But this gather and scatter operation, to me, it is kind of similar to these the way the decoupled access execute works. The access part, doing the gather and scatter, it gather the data, it scatter the data back. And then the execute part actually process the data. And so over here is how it works. So there's a instruction and E instruction. The A instruction is the access. The E instruction is the execute. A instruction basically would do all the read and writes to the memory. The data that I read is put in the queue so that you can execute that data. Data put back into the write queue, right? The write queue would go to this write access queue and being put onto the memory. And that's it. And then to make sure that you have some control elements, you also have the queue, there's two queue that synchronize the register for both sides of the processor. And this allows you to actually say, okay, is my element ready? If it's ready, take that element from the queue, execute it, send it back. If my element is not ready, don't let them block the queue. Just stay there, say it's not ready, but you can take a look at other elements. So this is kind of like imitating out of order processor. When my data that I'm trying to access becomes ready, I'm going to execute it. What are the trade-offs? Basically, this is actually less complex than out of order processor, right? The execute stream can run ahead of the access stream. The access stream can also run ahead of execute stream. Whoever is faster would keep doing its job. Disadvantages are basically it's complex to design a compiler for this because you need to access instruction and execute instruction. You need to basically also partition the program and manage that queue, right? And branches become synchronization bottleneck, which actually can lead to performance degradation. It can be bad for performance. The next thing I need to talk about before we move on to very large instruction windows or VLIW is let's talk about how we fetch instruction in the out of order processor, right? Remember the instruction windows? Anyone still remember the instruction windows? What is an instruction windows? All right, in class exercise time, can one of you tell me what's the instruction windows? We covered that in the out of order scheduling lecture. It's a set of instruction that is ready to be dispatched in an out of order processor. Basically, the instruction that you just fetch and decode, but you haven't put that in the execute stage. You fetch, you decode, but you haven't put that in the execute stage. So it means that as a scheduler, I have a choice, right, on what to issue. That I have the windows, so I can pick what to issue. So what are the ideal choices? What are ideal choices? So let's assume there's no data dependency and there are 10 instructions that have no data dependency. My choice would be things like, can I try to reflect the data flow graph and pick the instruction that is most likely that everyone would use it? Shorter cycle for instruction can be so to address your comments. Shorter cycle instruction, yes, that can go into one of the consideration. Basically, if it's fast to execute and you finish it quickly, well, you have the data ready for the next instruction quickly. Most likely to be needed in the future is good candidate as well, because somehow you know that the instruction in the 10 instruction in the future need this data. If there are many consumer, basically it means that I produce the data that a lot of instruction needs. That is a good target as well. So what if there are multiple types of the ALU? So what are the common ones? Adder, multiplier, things to do logic, shifting, XOR, and right, division, subtraction. So what if there are multiple types of ALU? The question I want to ask you is, in the modern processor, there are actually multiple types of the ALU, right? So the design goal, this is kind of like the common design goal in architecture. If we add something as a hardware component, we want to fully utilize it. It should be cost efficient. It's similar to when you build some building, right? If you want to build a building, you want to make sure every single room has certain benefit. You don't want to add a blank room where you walk in and like, what the heck do I do with that room? And to be honest, because I'm looking for a house right now, I was visiting a lot of like this housing projects. And to my surprise, there's actually a lot of houses where I walk in and I question what the heck do I do with that room? It's too small to be anything useful. The ceiling is too low to be anything useful. I can't use it for a storage unit. There's no window in the room. Like there are so many weird things that are in the house that I'm like, Why do an architect build this room? Because sometimes they just want to actually build additional bedrooms so they can put additional number. They have 5 bedrooms and 4 bedrooms. Those things are useless. And as an architect, you should minimize useless stuff, maximize utility. This applies to both real world architects and computer architects. All right, I'll stop complaining about house search. So question to ask is, we want to maximize every single thing that we add to our processor, right? So the main problem is how to do it, right? Because the design goal is easy to figure out. We want to get the most benefit out of everything we add, but the main question is how do we do that? The first thing you need to do is you need to be able to model dependency between instruction. And you need to figure out what can be scheduled together, right? What can be scheduled together? What is the problem with the typical out-of-order processor? Because out-of-order processor allows you to figure these things out, right? You can figure out the dependency and you can figure out what can be scheduled processor through things like register renaming, future files, the reorder buffer and all those things. So what is the typical problem? It requires a lot of hardware. Instruction window is a table. Reorder buffer is a table. So many things that are there to support out-of-order processor is a table. So you can't have unlimited size, right? Everything requires transistor. So at some point you will have limit on what you can do. Everyone with me so far? If you have out-of-order processor with a bunch of ALUs, you want to maximize all the ALU usage. The problem is out-of-order processor has limited windows. These days, between 64 to 256 instruction window is still not perfect, right? Here come VLIW. It kind of like is a concept that involves both compiler and the hardware architecture work together to make things fast. So before we go to the VLIW, any questions from what we covered so far? Yes, no, not sure. Everyone's so quiet. How about this? Let's all go get coffee and we'll be back in 10 minutes. Is that okay? All right, so let's take a 10 minutes break. Let's meet back at 1:05. I'm gonna go get coffee. You all should go get coffee too. And I'm hoping my cat will not walk on the keyboard. So if I disappear, please assume that my cat walked there and somehow disconnect this connection. I'm gonna be back whenever I have my coffee at around 1 o'clock. And we'll meet again at 1:05, okay? All right. So quick break. We'll meet at 1:05. If I disconnected, I'll be back. It just means that my cat walked here on the keyboard. Literally like this. Already happened this morning. All right, I'm back. Are you guys back? Okay, so let's talk about the concept called very large instruction window, VLIW. These are one of the techniques in hardware that you might run into in on your job if you have to deal with the compiler and the hardware a little bit and to squeeze out performance. Sorry. All right. By the way, the PM 2.5 is coming again this year, so wear a mask. Yeah, I know it's the winter again, so winter is coming. Yeah, hopefully it's not as bad as last year, but it's still bad. So take care of your health. Not sure if we need more lockdown, but we definitely need to sort out how to take care of our environment. It's it's a thing, and I don't know why the government haven't really do much. So we'll see. Well, we know why the government haven't been doing much. I am not going to talk about it because it's my yes, it's not my job to talk about those. But I think you all know my opinion, uh, which is they do a bad job at what they're supposed to do. Okay, let's talk about dynamic instruction scheduling. Uh, Basically, in an out of order processor, instructions are scheduled dynamically, right? The scaling decision basically tries to maximize all the ALU utilization, hopefully making sure the older instructions are retired so you can move on to the next instruction. Make sure that dependent instructions are prioritized. So we'll talk about the last bullet point a little bit later. But the first downside is, as I said, this limited instruction windows. The second downside is this is complex. The reason why this is complex is because the comparisons, every time you need to do a compare, you need to add logic. Every time you need to actually figure out who needs what, you need logic. That logic means you need to add transistor. There's so much transistor that can go into your processor. So one thing you might have realized, you might have heard about smaller and smaller transistor, right? It used to be, well, our computer is using things like 190 nanometer, 85 nanometer, then 50 nanometer, 15 nanometer. These days you're looking at 5 nanometer, 7 nanometer. It's so small. The benefit of having such a small transistor is you can squeeze more in. When you have more transistor, you can make a bigger windows. You can make a bigger table. You can make a bigger cache, right? So there's actually benefit to having small transistor. But one thing you can do to help is what we call static instruction scheduling. This is done through the compiler, basically instructions that are ordered inside the memory. What we can do is to actually order them in the compiler, right? You compile your code, you use the compiler to perform analysis on your code. When you perform that analysis, you kind of sort, basically pre-sort the dependent instruction, making sure that subsequent instructions are not dependent so they can put in multiple ALUs. So so if you have a really simple compiler, typically what they do with your code is convert the code in C directly to assembly. If you see if else, compare branch. If you see add, compiler would add. If you see multiply, compiler would perform a multiply. It will not try to do something like if you do multiply by 4, instead of multiply, compiler would shift. right? A more complex compiler can do a lot more things on your code because of this. Syntactically, as long as the compiler understands what you are trying to do, as long as the compiler understands semantically what are you trying to do in your program, and as long as the results are correct, it doesn't matter what are the order of the instruction, right? So let's do a quick recap on DAG. Direct acyclic graph. So what does DAG mean in algorithm? Direct acyclic graph. What do they mean? Directed graph with no cycle, right? Anyone has any question about what is a directed graph with no cycle? Basically, it's a graph where each edge has a direction, and there's no way in this graph that I can draw a cycle. Why is that useful? Basically, DAG is applicable to instruction scheduling, similar to the data flow graph. Right? But this kind of looks similar to your data flow graph. You have an instruction, it produces something to the next node. If there's a direction, it means there's data dependency. If there is no path, it means that the instructions are independent of each other. So let's mark this as 1, 2, 3, 4, and 5, right? If you look at just 4 and 5, these are independent, right? You don't need to run 4 before 5 because there's no path between 4 and 5. There's no prerequisite. Are you familiar with prerequisite? When you need to enroll in the class, it means that you need to finish the first class before the second class, right? So those are the concept behind prerequisite. This is the same thing, right? Oops, same slide, my bad. So you can use DAG, this direct acyclic graph, to represent instruction, right? Yeah, top sort. So basically, you can have the first instruction that produce the result to the second instruction, which produce the result to the third and the fourth instruction, right? Which then produce the result as an input to the fifth instruction. You can have the sixth instruction right here, 7, and that's the eighth instruction and 9th instruction that's not depending on anyone, but they produce instruction to node 10, which produce to node 11, right? These are lines in your assembly code. Input means that I will need to read that value. Output means that I'm producing the value, right? Any question on this? Okay, so let's move on a little bit. Now that you know that we can represent instruction in the graph, right? We can represent instruction in the graph. The next thing is a recap on instruction word. What is inside the instruction? Opcode, operands, right? What if we can pack multiple instruction into one thing, into one long instruction word? And okay, don't walk on my keyboard. All right, so hi. We can pack 2 or 3 or 4 instruction into one single instruction that you fetch. This is different from SIMD. SIMD is one instruction that look exactly the same. Add. Over here is 4 different instructions, but we fetch them all together. Any questions so far? Any questions so far? Before my cat jump on my desk again. Okay, if there's no question so far, the benefit here is this. Some of the scaling decision is now can be done in software. Why? I can do this by scheduling some of the instruction into the first slot, second slot, or the third slot, or the fourth slot of my instruction word. You use the software to pre-pack the set of instructions that are not dependent, that are independent, my bad, independent. Instructions that are independent can be packed and scheduled at the same time. And this is done by the compiler. So you don't need huge instruction windows in the hardware. And then you can basically issue them to the decoder. So here's what VLIW is doing. You create multiple functional units. In the ALU, there are multiple types of ALUs: add, multiply, logic unit that do shift and or XOR. There are another one that do subtract, which is also capable of doing the compare, right? If you can subtract, it means you can compare. A jump instruction. Each one of these ALU would be assigned to different slots inside my instruction. Compiler would go search your code. Basically, you search your code to find independent instructions and provide this scheduling so that they map to the ALU. Within the same instruction, you have add, multiply, compare, jump, add, multiply, load, add, multiply, load, store inside one word. That's why we call VLIW, very large instruction word. Very large instruction word. Each group or bundle of this instruction are executed in lockstep. This is kind of similar to the GPU where you execute all the entire instruction word together. Instruction within each group are again statically aligned by the compiler to directly feed to the correct functional unit, right? If you don't have anything inside that particular ALU, then you put in no ops or no operation. And here's an example of this paper called Very Long Instruction Word Architecture of the ELI 512. This is actually one of the machine. ELI stands for enormously long word instruction, which consists of 512 bits. Back in the day, we're not that creative with naming, so but still, it tells exactly what the design is, right? A long word instruction that consists of 512 bits. So here's a high level design. Let's say this is your PC inside the memory. So memory is store your instruction, right? The PC, let's say, point to this line. Over here, each processing element, these exact order, it means that processing elements would be the adder. This means it's a lower store unit. This processing element would be multiplier. And this would be also the basically this in the ALU you don't have to do much. Basically you forward R8 to R9 because basically this means you're moving data. Right? So it means that for all instruction in the first slot, everything here has to be an add. Everything here has to be a load or store. Everything here has to be a multiply. Everything here has to be a move. So it has to be aligned in this way, right? So can someone tell me what is the benefit of doing this? What's the benefit of doing this thing? Uh, Actually, this is not as complex ISA to some, well, it can be complex. The benefit is now you finish 4 things in one cycle. So you have an adder and multiplier, you utilize all of them in one cycle. So you have better ALU utilization, right? What's the downside of this? It means that somehow my PC, that one instruction, you need to go and collect who can do an add, who can do a multiply, who can do a load, who can do a move, and put them in. So if there's a code with a lot of dependency, these things might turn into a bunch of no ops, right? No op means I'm not running anything in this slot. Which reduce the efficiency of the VLIW processor. And as I have the arrow sign pointed down here, it means that basically the adder would be forward to processing element 1. It cannot go to processing element 2 because it's a totally wrong ALU that has nothing to do with each other. Instruction sent to the processing element has to be the correct type. So here's some discussion for the class, right? Well, we already talked about the trade-off. More throughput, more complex design, right? The complexity now comes from the compiler instead of instruction window. So you reduce the burden on the out-of-order processor because it's already been pre-compute. But the compiler would have to run and compile your code for a while to actually extract everything. So what if there are branches? Yay, fun. So if you have branches, then you are likely to input no ops everywhere. What if the program is not parallelizable? Again, no ops everywhere. Each PE has to be a different ALU unit. Yes. So this is our requirement. Basically, in the out of order processor, this PE 1, 2, 3, and 4, we would treat them as one single ALU, right? One single ALU, where if you have an add operation, you would just take the adder. If it's a multiply, it would go to the multiplier. Over here, we can say, okay, since we have an adder and a multiplier, I would make sure that I can utilize both of them by going through my assembly code and find that instruction that can utilize these processing elements. So does it answer your question? Okay. So here, what if that branch, a bunch of no ops? What if program are not parallelizable? Again, a bunch of no ops. Modern VLIW processor, this is like an interesting discussion part because of these reasons. Anyone heard of IA64? No, I assume. Yes. How about this thing called x86-64? Anyone heard about x86-64? Yes, no? It's the ISA we use for the file processing and the system skill class. It's the x86 instruction, but for 64-bit machine. So that's the x86-64. The x86-64 is actually called AMD 64. Do you know that the one you use for both Intel and AMD processor is the ISA coming from AMD? Anyone know that? Or this is the first time you heard about it? Yes, no, I just want some response from you guys just to realize whether you're here or not. This is the last slide, sorry, since we have time. How about Intel Itanium? Oh, have you heard of AMD 64 and x86 64? And the answer for x86 64, if you take file processing, or if you take the system skill class, the assembly code that you've seen, those are similar to x86 64. Those are AMD version of x86 for 64-bit machine. The 32-bit machine, that was an Intel version. Intel was trying to push IA64 for VLIW. That's the Intel answer to 64-bit machine. Trying to push this architecture called Intel Itanium, right? Back around, I think, 2009. This is not fully VLIW, but it uses the same principle. They have the instruction set called Epic. It was a big thing. And it's actually, technically, it could have been really good, right? It could have been really good. It allows dependent instruction to be merged into a bundle, and you can extract dependency. And this failed because of this one problem that I want you to realize. Whenever you develop a new ISA, you need to make sure they are backward compatible. What do backward compatibility mean? Anyone want to give an example? What is an example of like something that's backward compatible? Yep, it should work on an older version of the software. It means that if I have Microsoft Word, I want to make sure the same Microsoft Word works on this new ISA, right? This is why it's so important for Apple. So I'm not sure if you heard about the new MacBook that will use ARM ISA instead of Intel ISA. Yeah, so those new MacBook, it better be providing backward compatibility, right? They better provide backward compatibility because you are going to be royal. Like basically, all the user will be really angry if they buy those MacBook, which always going to cost a lot of money, right? But turns out cannot run the old version of Microsoft Office, which is also cost you a lot of money. So this is one thing that you must do when you develop a new ISA. You need to, well, fundamentally, you can use a compiler to fix the problem, right? You can provide backward compatibility. The problem at Intel during the time is AMD came up with the 64-bit version of the ISA, and they are backward compatible. So AMD 64 take the market by the storm. Everyone say, hey, I would benefit from having more than 4 GB of memory, right? If you use 32 bits, it means that your DRAM can go up to 4 GB. Nowadays, all your laptop is greater than 4 GB. So when AMD 64 came out, everyone adapts to the new ISA. Why? They are backward compatible. So all the machines now use AMD 64. Even Intel processor use AMD 64 ISA. Why is that the case? Because everyone else use AMD 64 now. And they are backward compatible. You can run a 32-bit version of the program and it would run properly. So you can install I don't know, Microsoft Office 2007 and it would work out of the new CPU. that is written on AMD 64 ISA. What I'm expecting from the new Apple laptop, if I buy one, that the one that has the ARM processor, I would expect them to be backward compatible as well. So this is one of the really important aspects when you come up with a new ISA, right? You want to make sure that if you have programs that run earlier, it's supposed to run now. Any questions so far? Because this is actually the last slides we have right here. I wonder how the sharing of the battery across Apple device works. Oh, wait, how? Apple device can share battery? Like in what way? I did not know that. Oh, it's coming soon. Huh. So is it like you plug in the USB cable and they can now charge the other device? Okay, so I'll be excited to look at what they do, but I guess my expectation is probably things like when I connect the USB 3 together, right? There's a likelihood that I can share the battery in a sense that if my laptop run out of battery, I would use the pen. So the USB cable, do I have one here around me? Nope. But you see the pins, right, inside the cable? Those pins, some of them are actually like providing the input voltage. That's why you can charge your battery, right? So it means that you might be able to, in theory, right, charge uh, charge the battery into the machine that needs the battery. And with that, when you connect the two together, you are basically enabling the fact that you be able to use from your laptop, you'll be able to use your iPad's battery. That's my guess. That's my guess. I'm not sure what they'll come up with. So that seems exciting, or at least interesting. Any other questions? Yes, no? No questions? Okay. Anything from this lecture that interests you and you want to discuss, because we have like maybe 15 more minutes. Otherwise, I'm gonna move on to the discussion over the last assignment. Let me save the PowerPoint first before I talk about this. So here's what lab 3 would entail. I'm gonna release the lab. Good. Should we make some random operation legs longer than others? No. So basically, all the execute, anything that has to do with execute, make them take the same. For simplicity, everything take one cycle. This is for your own sanity. Basically, everything take one cycle. Fetch one cycle, decode one cycle, execute one cycle, memory one cycle, write back one cycle, regardless of what the operation are. So does it answer your question? Okay. All right. For lab 3, the interesting things is, well, actually, there are two interesting things. First of all, it's about 3 weeks left, and I don't want to heavily burden you with like a new lab, right? And lab 3, you will start fresh with my own implementation of pipelining. So you can start from there. There's no need to finish lab 2 before lab 3. I hope that helps everyone here, right? What I'm gonna propose is instead of having basically instead of having these like the default part that you have to do and the extra credit, there'll be a lot of extra credit instead, because one thing I realized is with lab 1 and lab 2, there's a really high likelihood that some of you here will not be able to like kind of like get out the score that you would like to have. And this will not impact how hard the final would be. Right? So this is basically all for your benefit. I'm gonna allow tons of extra credit. Most of the work done here will be revolving around range prediction and caching. If you already do lab 1 and 2, what you need to do for lab 3 is figuring out, do I need those extra credit? If I do need those extra credit, please check them out, and I'll have points assigned to each task based on how hard it is. Then I'm gonna basically grade them. As I said, huge fraction of that will go to extra credit. I've been listening to some of the feedback on the class, and everyone was surprised about the lab because there were no labs for this class whatsoever. And I don't feel like that's a good way to learn architecture. Or at least that's not a good way to learn any computer science classes. It's bullshit to have no assignments, no labs, right? And I don't want to run a class that way. So I come up with the lab, but it's hard. I realize that, and I know that it's hard ahead of time. So I want to make sure lab 3 would be kind of like, okay, if you somehow screwed up on lab 1 and 2, you will use lab 3, which I give you actual fresh start. You have a static code. You will build caching and branch prediction on top of it. And then based on that, depending on which part you get correctly, you'll be given extra credit. Anyone hate this idea? Let me know right now. And the way I'm going to calculate the assignment's grade out of your entire grade is this. Basically, all the non-extra credit part will be basically go to the 100% of your assignment grade. Anything going to the extra credit will be added on top of it. I will have my local version of my grade sheet because I basically cannot put in more than 100 points on your final grade sheet, right? So if you do all the extra credit and you want to try all these tasks, awesome. I would love that. And you learn a lot. And you are likely to be able to screw a lot, like make a lot of mistakes on your final exam and still get 100. If not, if you basically say, hey, I need to catch up and I need to graduate by passing this class, lab 3 is a good way to make sure you can do that. Anyone with me? Anyone don't want this? Who wants this? Okay, so at least one person wants this. Okay, so basically it seems like most people agree on this policy. So this is kind of like me being, so I also, as I said, this is the first version of this class. I want to be more lenient. So please make sure you have time to work through lab 3. And yeah, of course, you can find nothing on Google on the lab because I came up with it. There was this material, we came up with it together when I was a TA at CMU. So obviously we don't post solutions. So if you have question, come by during the office hour. Is it? Oh, okay. Okay. So, well, hopefully lab 3 with the starter code. Hopefully those are easier for you. So with lab 3 material, I'll tell you exactly how each of these elements should be modeled. And most of them will be extra credit, as I said. So please be aware that these are free points that you can use to catch up. And hopefully your grade will not be screwed by how hard my assignment is. And I would need to kind of readjust afterward, right? On other things that are not clear, I would like to hear from you. So one thing I'd really appreciate after we're done with this class, after your grade has been submitted, I would like you all to kind of like give me a feedback on fractions. Basically tell me for the assignments which parts are not clear, which part I can explain better so that for your underclassmen who are taking this class next semester, they are going to have fewer extra credit that I can guarantee. But hopefully the assignment sheet will be improved to make it more clear on what they need to do. Because this is one of the downside I found from releasing lab 1 and lab 2. I think I did not make it clear enough. So I feel like that's one thing I can improve, and I would really appreciate your feedback after the grade are submitted. The reason why I said after the grade are submitted is just to make sure if you fear that there'll be like repercussion on whatever you say, I don't care. I want to improve my own class, right? So please be critical. I live my life benefiting from critiques, so I would love to hear things. And sure, if you want to pass, okay. So if you want to pass the class, then go and do lab 3. If you feel that you're not good enough. For jump and branch, do we have to update the PC only when it's in the write back stage? If you know that, okay, let me put it this way. If you have data forwarding and you know the target of your jump and you know exactly at this point you can update the PC, you can update it at the earliest stage of the basically as early as possible. There's no reason to stall if you don't have to stall. The lab 2 pipeline with stalling, just stall until you know the result of your branch. Typically those would be in the execute. But once you pass the execute stage, you know where you're branching, then you update the PC. The next fetch instruction go into the pipeline. So does it answer your question, or is it more confusing after my answer? And by the way, I'm gonna release lab 3 whenever lab 2 is due, because I give you starter code that include pipelining. I don't want you to submit that as a solution. So sorry about that. I need to make sure that happens. Uh, does it end up so champ? Does my answer, is it clear, or are you still confused? Are you there? Oh, what if the update PC depends on previous instruction? Basically, for the stalling version, that's a write back. So once write back is done, you write the correct value, then you update the PC. If you do data forwarding, then by the time execute stage come in, you know the result already, so you can forward it back. So as I said, that's why it depends on, are you implementing the stalling version, which is not the extra credit part, or the data forwarding version, which is the extra credit. Does it clear up the question? Basically, if you're doing the stalling, wait until write back. Otherwise, wait until the earliest that you know the data and you forward it back. All right, cool. Any other questions? Okay, so if there are no more questions, basically we'll wrap up today's lecture right now. And so let me stop recording. I'm gonna post all the videos for both more Monday video and today's video sometime later today or tomorrow. If I forgot, please, I ask of you to remind me. I don't mind getting reminded at all. I just want to make sure I don't forget.